Hello and welcome to another podcast. I believe this is number 27. At this point, I've lost count, so I don't know if it matters, but let's just call it 27. And I'm always curious when I look at the dialogue listing if they list it as a podcast with a T as opposed to a podcast with a P. But that's neither here nor there. What is here is we're continuing on with the kinetics we'd had. So this is the thermodynamic kinetics section. I did the transition last time. Kinetics is study of rate. And this time, what I want to do is just go into all the features of kinetics. And I will say, of what we've done so far, this is one that will have the most relevance to OChem. So the previous stuff was GChem review with a little bit of OChem infusion into it. This is, again, GChem review, but very applicable. So reaction order. In OChem, we won't really see zero-order reactions, but I still want to address it, so it'll help us to understand first and second order. A zero-order reaction is one that the rate is constant. No matter how much substrate, how much reactant you put into the system, the rate is going to be constant. So we usually see this when we have a catalyst. Catalyst can take on a reactant and convert it to product, but it can only do it at a certain speed. So even if you add more and more reactant, there's only so much catalyst to be able to crank it through. You're going to notice I'm going to use the word substrate, a biochemistry term, and reactant, OChem, organic chemistry, general chemistry term, interchangeably. So I apologize in advance, but substrate is a biochemical term to describe a reactant. Enzyme and catalyst, I'm going to say, are synonymous for my purposes, although the reality is an enzyme can also align a molecule with specific stereochemistry. It can help molecules to facilitate a certain orientation that it needs for both reactivity and the product you spit out. So enzymes are more complex, but I'm going to, again, use them interchangeably, and then product is product. So zero order, constant rate, because it turns over to a certain rate. First order, we start getting a little more interesting for chemistry. This next chapter we're going to get to is going to really emphasize first order. So first order is where it only depends on one thing. So if you have two things reacting, A plus B, A must do something first to be able to react with B. So the rate determining step, which is what RDS stands for, only depends on one of the reactants. So it's a first order reaction. So perfect example that A and B again, let's consider this. So when A doubles, when A goes up by 2 and there's no change in B, we see a twofold increase in the rate. So 2 to the first power equals 2, meaning the rate doubled because the rate determining reactant, A, doubled. But in trials 2 to 3, no change. This one doubled, but the reaction experienced no change. So even though this doubled, we saw no change in the reaction rate, it stayed the same, which meant it did not depend on B. So specifically for this one, we would state that the rate is equal to K, some constant, depends on all the environmental factors, temperature, solvent, miscibility, how it can move around, alignment factors, everything. But for now, I'm just going to say a K. So rate depends on A. A is the one in the rate determining step. Okay, second order depends on two things. I've listed it as R squared, and that is one case. So it could be A combining with A to form some intermediate, and that intermediate reacts with B. But it'll also be A and B coming together. Both of those are defined as rate determining or second order rate reactions because they both depend on two molecules for the rate determining step. So whether it's A squared or A times B, those will both be second order. But I would say, as we will here, let's look at this. The same story as before. This rate, 2 times, no change, and 2 times, just like before. But this time, this one, no change, 2 times, and this time, this is 2 times. So now it depends on B. So increase of B doubled, the rate doubled, so it's first order with respect to B. In the between trial 1 and 2, the concentration of A doubled, the rate doubled, so it's first order with A. But overall, we're going to say it is second order. It's first order with respect to A, first order with respect to B, but overall second order. And so the 2 in green are going to be the important ones because a lot of our OChem reactions, when we look at the kinetics, will either be one molecule breaking apart and becoming reactive, or two molecules coming together and carrying out a reaction. So we're going to focus strictly on first order and second order for this class. Intermediate orders and the more complex kinetics you can get into when you have multiple intermediates, we're not going to worry about that at this level. Biochem, you'll worry about it a little bit. GChem was where you worried about the most. And then ultimately, if you go on, if you're a chemistry major and you go on to PChem, you'll worry about different orders, like intermediate orders and pseudo orders. Not for us. We're first order and second order. And I'm going to just give you a little lead in. This is an SN1 where the electrophile, one of the molecules, has to break apart. The leaving group has to leave from an electrophile before the reaction can occur. So the rate determining step is at leaving. So it only depends on the electrophile. The other one is going to be SN2. The reason I bring this up, this one, first order, this two, second order. That's going to become key. That's why we're doing the rates. Okay, colorful screen that I'll move away from. Typical graphs, more of them. So we just graph like crazy everything. But this, I think, is pretty important in general. So this is going to apply to pretty much every science. We love graphing things. We love looking at math. So for zero order, it's just a constant rate. So at time zero, let's say we have 1 molar. If it loses 0.25 molar every unit of time, let's say the second, a minute, an hour, whatever this is, doesn't matter. If I lose 0.25 in the first unit, I lose another 0.25 between 1 and 2, so another 1 unit. From 2 to 3, another unit of time, and I've lost another 0.25. So it's a constant decay. So in this case, the rate is just constant at 25 or 0.25 molar per second or per minute or per hour or per day. Okay, happy with that. First order, on the other hand, what you have to recognize is the rate depends on the concentration. So the concentration goes down, the rate goes down. Although this is a calculus-free class, you should know this about calculus. The tangent is the instantaneous slope at any given point. Oh, this is... Okay, you're just going to trust that these are somewhat straight lines. Tangential lines, actually, but wow. Okay, rather than watch me fail at this over and over, know that the tangent is here, tangent is here, tangent here. So it's going from steep, which means it's fast, to medium, which means it's medium, to flat, which means it's slow. So the tangent, which I'm going to erase my terrible lines, tells me roughly what the rate is. So it goes from fast, medium, to slow. So over time, the rate's going to go from fast to medium to slow to non-existent when you run out of everything. So notice that in the unit of time, it changed by 0.48, then it changed by 0.24, then it changed by 0.12, and then 0.6. So the change keeps decreasing. In fact, if you notice, it's changing uniformly. Changes by 0.48, then it changes by half of 0.48, then it changes by a quarter of 0.48, then it changes by an eighth of 0.48. So you see some sort of mathematical trend that it gets less and less constant, or as it gets less and less concentrated, it gets less and less in terms of its rate. So the rate decreases linearly, but the actual concentration follows this curve, this asymptotic curve. Second order decay, I want to go ahead and look at this again. Notice that's a 0.65 change. That's massive. But notice this one is 0.10. This one is 0.07. So it decreases, but decreases much more drastically. So this drops very fast at first. So whereas this may not be something that I'm going to get into in any detail in terms of this class, important to know. So I know a lot of you want to go into some medically related field. No matter what you're in, eventually you're going to have to give a patient some sort of medication, some sort of anesthetic, some sort of like non-natural drug in their body. And you have to worry about how it decays and how long it takes to get into the cell, how its efficacy, and how it clears the body. All these things become key. So if you give somebody a second order drug, by the time it gets in their cell, it's deplenished to such a large degree that you don't have much. So with a second order drug, you give them a massive dose to begin with, so that down here, let's say this is its efficacy concentration, by the time it gets to the cell, you're good, but then it stays there for a long time, doesn't diminish. So big dose, but not very often. Zero order, for instance, if you have a drug that follows zero order decay, it decays slowly, so therefore I'd give them a small dose, but they run out, so I have to redose them. So those are usually something you have every few hours, but a small pill. So horse pill, small pills, but high frequency. So not that this is pharmacokinetics, but that's where OChem is just really helpful in understanding, and GChem in this case, really helpful in understanding drug efficacy. So you have to know the efficacy, the migration rate into the body, just all these things start to become just an interesting puzzle. Okay, back to this, decays very quickly. This one decays, the rate's gonna also decay. The rate slows down at first, but then it stays steady at a really small value. Last but not least, half-life, the time it takes for something to decay to half its original value. From 100% to 50% takes a certain amount of time. From 50 to 25, so from 100 to 50 is 2 units a time. From 20 or 50 to 25 is 1 unit at a time. And then to 12.5 would be half a unit at a time. So the amount of time it takes for each subsequent half-life keeps on going down. Whereas for first order, it's famous for the fact that half-life is constant. So my lines, I'm looking at them, don't look all that straight, but that, believe it or not, is a straight line. So that goes here, this one goes here, so you get equal half-lives. Half-life is constant, and then for the last one, half-life is actually increasing. So you get it loses half very quickly, then slowly, more slowly. So second order medicine, second order drugs that you give a patient will linger in their system for a long time, so you can test for that metabolite or test for that compound days later, weeks later, possibly months later. Whereas zero order clears the system, first order clears it, but not as fast, or faster than second order, but not that fast. Okay, that was a tangent. Back to how we apply it. So let's say we're talking about whether I need to decide if something's an SN1 or SN2 reaction from the data. So does it depend on just A, or does it depend on A and B? So just like before, what we did is we looked at what happens to A. So A goes up by a factor of 2, no change. And this goes up by essentially a factor of 2. So A to the first power, 2 to the first power equals 2. So it definitely depends on A to the first power. As a consequence, we can get rid of choices B and D. Now the question really comes down to, does it depend on B or not? Which is exactly what we expect for OChem. Is it SN1, it only depends on electrophile, or SN2, does it depend on electrophile and nucleophile? So the fact that B goes up by 2 and this number changes means it has to be C. But real careful. This is a 10 to the minus 2. This is a 12.3 times 10 to the minus 3, not a 1.23 times 10 to the minus 2 when comparing. So if I make it a 10 to the minus 3 instead of 10 to the minus 2, this goes from 6 to 12, which means it did in fact double. So best answer, C is depends on both A and B. Okay, not a bad question. Again, I'm going to just make note, that would be an SN2 as opposed to an SN1. Okay, other thing I want to bring up, mention the fact that K depends on all these other things. So what will change? Well, the concentration of a reactant in the rate determining step, we know for sure changes because it equals K times reactant in the rate determining step. So that I know for sure. That's my freebie, my given. Does anything else make a difference? Does increase in temperature have an impact on it? Sure. Raise the temperature, more heat energy. More heat energy means more energy to overcome activation barriers. More molecules will be able to overcome it. That seems like that should help. Adding a catalyst, sure, we lower the activation energy, so now more molecules can overcome whatever threshold to react, so it should react faster. And again, adding more reactant in the rate determining step will always increase the rate if it's in the rate determining step. But adding solvent is an interesting one. So excuse me, solvent may affect the collision frequency, it could affect here, but it's definitely going to lower the concentration of this. And I so apologize for coughing today, it just happens to be one of those mornings. So I will try not to cough anymore, I hope. Okay, so rate determining step, the reactant in it, if you add solvent, you dilute it, that will make it go down. Okay, let's see what my pretty computer picture tells me. It tells me, as predicted, rate is going to equal K, some constant, times reactants in the rate determining step. Constant equals some so-called Arrhenius constant, which has to do with every factor that we can think of: how fast it migrates, how much it gets solvated, how often it aligns with the correct orientation, does it need to align with the correct orientation, all the factors of reaction that we don't take into account in terms of energetics come into play here. Activation energy over RT. This is all one exponent, by the way. It doesn't look very pretty, but e to the minus of this. So if we increase the temperature, T goes up. This exponent becomes less negative because if T goes up, the denominator is bigger, so this magnitude goes down, but it's negative. So it's now a less negative. So e to a less negative is like e to a more positive, makes it increase. Adding catalyst lowers the activation energy. So the numerator goes down, so this fraction gets smaller. E to a smaller negative number is going to be a bigger overall value. Adding more reactant just flat out raises that one right there. And then finally, adding more solvent, as mentioned, dilutes this concentration. Okay, so in choice A, we made this go down. That worked. B, we made that one go up. I said that completely backwards. My apologies. A, B, and C. It was in choice D where we made that concentration go down. Okay. Questions aside, I want to start looking at what happens from an energy diagram. This is now where we're really into hardcore OChem. We like going from a starting material to a product, but along the way, there's going to be different things can happen. So sometimes just something comes in, knocks something else out, like the substitution reaction we mentioned early on by an SN2 mechanism, very fast. It just comes in, knocks it out, no big deal. But here we have starting material that has to go up to what's known as an intermediate or transition state. And that's going to be one of the things we question. Transition states are brief experiences at high energy that we cannot isolate, we can't study. We just know it has passed through there because if it's here and here, it had to go through that point. As opposed to an intermediate is a low point where we can actually isolate it because it has energy to climb here and climb here. A small amount can exist before it climbs that barrier. So you can actually observe intermediates. Transition states, you can only theorize they must have happened. So really good example, if you throw something up into the air, if you try to say exactly the way it's aligned, so let's say you throw a penny in the air, can you, looking at it, tell me whether it's heads up, which way it was oriented, head, like what angle it's at, anything about it while it's in flight at its highest point? Probably not. But if it tosses it up there, hits on like a shelf up top before falling back down, you can at least tell me on the shelf which way it exists because it's there for enough time we can observe it. So going up to the top, hitting its highest point, starting to fall, that's like a transition state. We know it had to hit a highest point because it changed directions, but I don't know exactly what it was like when it was there. So I just theorized it had to. So starting material, SM, product P. Intermediate is going to be represented by an I on this. And then TS, transition state, but notice transition state 1 and transition state 2, meaning your starting material goes to an intermediate, passes through the first transition state, and then pass through a second transition state to get to a product. Questions that'll pop up, which is a bigger amount of energy from starting material to transition state 1 or up to transition state 2? Because this is such a massive climb, so much bigger than this, and even so much bigger than this one. As a general rule, the highest transition state is going to be associated with the rate determining step. So this is a case where first step takes high energy, high activation energy. So it is rate determining. Second step is trivial. If we can get through the first step, it's going to be able to go through the second step easily. So in this case, we have a very low intermediate concentration because once we make it, it can go to product very quickly. Had these peaks been different, had this one been low and then this one been high, then intermediate concentration would be a little bit higher going that direction. And basically, this well tells me how much it's going to form. But because of this, it's going to go forward rather than backwards. So intermediate is going to move to product more often than starting material or reactant. Okay, rate determining step, first step, we just mentioned. In transition state, short-lived, you can't observe it. Intermediate, you can. So how are they different? You can see an intermediate. So it can be observed, meaning you can use spectroscopy to detect it. this cannot be observed. That's pretty much the difference. We know it has to happen. We can swear we see it, but we don't really see it. It happens too fast for us. So impact of a catalyst. This one, I think, is just old news from when you took GChem. Here's my reaction. It has certain activation energy, goes to a product. With a catalyst, you lower the activation energy, so the reaction is free to go faster in both directions, but I worry about the forward. But you end up getting the same product, meaning it doesn't make the reaction more favorable or less favorable. It just makes you get to that favorable state or unfavorable state faster. So same starting energy, same ending energy, but a lower transition state energy. So the enzyme must somehow, or the catalyst must somehow be involved with that transition state, meaning it must find it, align it, and then send it on its way to the reaction. And by the way, a one-step catalyzed reaction, very rare. This is, I mean, I'm tossing in for simplicity of the picture, but usually introduces more complex steps. So it usually binds in the rate determining step of a multi-step reaction. Okay, so adding catalyst lowers the activation energy, but overall the reaction change of energy stays the same. And then faster, but the same quantity of products. Okay, so feeling pretty good about this. Competing reactions. So every now and then, a reactant and product can do two things instead of just one. So there's two possibilities for that outcome. So let's say one, the solid line represents one product, so it takes a lot of energy in transition state, but you get a more stable product. Dashed lines, it's going to happen faster, but it's going to be less stable. So it can go, remember, reactions go backwards. So if you have this situation, initially when you observe the reaction, you might see this compound forming. But over time, as this goes back and forth, this one can also go. And once this forms a product, it's harder for it to go backwards, so it sticks around a little more. So in the first few seconds, you might see 20%, I should say 80% of this, 20% of that. But after like double the amount of time, it might go down to 70 and 30. And given enough time, it might go down to 50-50. And then if you wait all day, it might go down to 2 and 98. So in time, you will eventually get what's known as the thermodynamic product. Thermodynamic product, the one that's thermodynamically more favorable. The faster one, the one that occurs because of lower activation energy, is known as the kinetic product, the one you get fast. So the kinetic product will form initially very quickly, but over time, that kinetic product will turn into the thermodynamic product. So if you want to get one product over the other, you can do it by messing with the temperature, the timing, when you extract things out, just everything about the reaction can be controlled by just trying to manipulate that difference or this difference right here. Okay, so A plus B and Q plus Z just to have some sort of product. And then the other one I'll put A plus B going to Q prime plus Z prime, the kinetic products. And so sorry I drew this in the way, but I'll just leave it up. So kinetic products are the less stable ones, thermo are more stable. Thermo are named more stable, or named thermo because they are more stable. Kinetic aren't named kinetic because they're less stable. They're named kinetic because they have a lower energy transition state. So slower reaction generates Q and Z. The faster reaction generates Q prime and Z prime. So you get these Q prime and Z prime quickly, but over time, you start seeing more and more Q and Z and less Q prime and Z prime. And then, as mentioned, reaction temperature. If I lower the temperature so that it can't really get over this very easily, then I can force it to take the kinetic pathway. And by not giving enough energy to go backwards, then I can kind of limit it to be this product. So low temperature, that's why I drew it in blue for cold, you'll start seeing a little more of the kinetic product. But given enough heat energy so it can go forward and backward, it will. Eventually, it'll go to the more stable compound. So temperature and time, both begin with T. Raise the temperature, add more time, thermodynamic product will be what you expect. Make it cold, cold begins with K, and so does kinetic. So cold leads to kinetic. So cold typically favors kinetic, and temp side typically favors thermodynamic. K stick together, kinetic and cold. T stick together, temperature and thermo. Okay, got to get rid of everything I just wrote. I apologize for bad space planning. Every now and then you have competing reactions like this where the more favorable product is also the lower activation energy. So the solid line has lower activation energy and finishes lower. Dash line less favorable and higher energy at the end, so that it's not as stable. So it's harder to form and it's less favorable to form. So therefore, it typically doesn't form. So E prime and J prime, you can't really exploit the system to get them. It's just going to happen. And so those are side products that are very, very small. So the other one, just purely side products, and you can manipulate, I'm sure, temperature depending on this difference and this difference to figure out what the optimal temperature is to get as much of this and little of this as possible, or conversely, as much of this and little of this as possible, but you'll always get mostly this and just a tiny bit of this. Okay. The Hammond postulate. Hammond postulate, like so many things that we'll see in just science in general, it's an easy concept where somebody puts their name attached to it and it sounds more intimidating than it is. Hammond basically said that if you have a process where you go from a starting material or a reactant through a transition state to a product somewhere down the line, that if it's a very high starting material and low ending material energy-wise, so high in the energy diagram, low, then transition state is going to be early in the graph and closer in energy and closer in shape, closer in everything to the starting material. Whereas if you have one that goes uphill, you have a tendency to have the transition state be more like where it finishes. So these graphs are not symmetric on the time axis, on the reaction coordinate axis. They always, the hump is slightly closer to the higher energy state. So notice if it did this, where it's exothermic, transition state occurs early. So we call that an early transition state. And then in the next case, where it goes to very high energy and it's really close to the end, we call it a late transition state. So the solid line has the early transition state, the dashed line has the later transition state. And your transition state structurally is more similar to the one it's closer to in energy. Meaning in this case, transition state is going to look more like the reactant that's slightly, I guess, denatured or deformed. This transition state is going to look more like the product, slightly deformed or slightly denatured. So not a big deal, and I dare say it's kind of common sense, but notice if the graph is symmetric, it should have a transition state right about in the middle. Early transition state means that's your higher side. Late transition state means that's your higher side. It really isn't a complicated concept, but again, because it has a name and the word postulate sounds so important, it could be intimidating. Okay, so I want to finish this up by taking these energy diagrams we've come up with and actually trying to look physically at how these reactions occur. So substitution at carbonyl, as implied from the name substitution, one thing's going to go on, one thing's going to come off. Early on in your chemistry, you need to start recognizing the thing that comes off is the one with the weakest bond. So carbon-carbon bonds are strong, carbon-oxygen double bond is strong, but a carbon to a halogen, because it's very big and highly electronegative, it wants to take electrons back, that's going to be your leaving group. And an atom with a lone pair is going to be your nucleophile. So nucleophiles are going to donate electrons, so our arrows always start from electrons, from where they are to where you want them. On this carbonyl, because of resonance, that's going to be delta minus, and this is going to be delta plus, because there's a minor contributor that has a full minus on O and a full plus on carbon. This lone pair is going to look for the biggest plus it can find. Minus, neutral, mildly minus, and then definitely that's a full plus there. So it's going to attack in this way. So these electrons are going there. When they do, that forms 1, 2, 3, 4, 5 bonds of carbon. So the weakest bond, sigma, 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 or pi. Pi bond's weakest, so it breaks that pi bond. And they have, or it forms what I'm going to refer to as, and it depends on the textbook. Some people say this is what you should call it, some people don't. So note that I'm going with just the way I learned it, and I'm going to keep repeating it. This is 1, 2, 3, 4 things attached to the central carbon, so they call it a tetrahedral intermediate. From there, the negative charge can kick back in and can kick out this leaving group. So it is actually happening in 2 steps. You're going from this coming in and kicking up to form this tetrahedral intermediate, which kicks back in and kicks that Cl out. So the Cl is going to be dangling over here as a Cl minus. Okay, where the controversy comes in is, again, the definition of an intermediate versus a transition state. So I am in the camp that believes you can actually physically see this. You can using spectroscopy, you can identify that bond in particular, but you can identify this molecule. So I call it tetrahedral intermediate, but there are those who say, yeah, you can't really see it. You're lying to us. So again, just whatever it might be. I know I'm probably getting way into more detail than we need, but in case you ever see this in the future, and somebody refers to it as a tetrahedral transition state or carbonyl reaction transition state, fine. Just go with whatever the information is. But for my perspective, anything I write, I'm going to always call it tetrahedral intermediate. So that's a substitution into carbonyl. One thing's going on, the other thing's leaving. What we're going to learn is every now and then, you don't have a leaving group. So if there's no leaving group, then it's going to do the same thing. This nucleophile is still going to come on, but when it does, it's going to break the pi bond. So the exact same first step, but there's nothing to kick out. So it's just going to end up going to this tetrahedral intermediate like we had before, except now there's nothing it can do. So it ends up this O negative. I could say this is it, but if the solvent has any sort of protic nature to it, if the solvent can release hydrogen, then it can do that. So putting just an H plus technically isn't correct. It has to be bound to a solvent. You can't, it just doesn't freely move around. And there could be a plus on this group, or it could be negative solvent with positive H. But whatever it is, it could be just a neutral or a protonated compound. The point is this O is going to pick it up. And so ultimately we added across a carbonyl, meaning if we look at the original carbon here, it had an R and R prime and an O. Now it has an R, R prime, O, but a C. So CN came in. And then the O had just 2 bonds of carbon, just had the bond of carbon like it has here, but it also has an H. So we in essence added an H and a CN. So this is called addition because both of them have gone on. The first one is called substitution because one thing came on and something came off. So the leaving group is off by itself here. This one has no leaving group, so nothing kicks off. So you add so-called across that carbonyl, across a pi bond. We are going to go through so many mechanisms starting right this second that it's going to become really overwhelming. So your job is to always remember the basic rules of it. You start with something with a lone pair, and it attacks something with a delta plus. So negative finds positive. Delta minus with lone pair is going to find delta plus with the need for electrons. So a nucleophile is going to find electrophile, and if it has a leaving group, the leaving group will be kicked out eventually. If there's no leaving group, it'll just add across. You are going to see this so often in so many different ways with so many different molecules. It's going to feel overwhelming, but at its core, it's actually a pretty straightforward, and I would dare say, simple concept. So this is where we officially transition from going over review of GChem here and there, talking about different concepts from different areas, trying to piece together the stereochemistry, the charge distribution within a molecule, like we talked about with resonance, how reactive something is, we talked about acidity. All those pieces of information we covered up to this point are all seemingly individual and sort of stacked together, and we're just learning this pool of information for who knows what reason. Starting next chapter, starting chapter 7, we will see the reason. Everything's going to hopefully start to become a little more clear. So with that, I want to end this. So this will tie off chapter 6, and we'll go into chapter 7 next time. Have an absolutely wonderful, wonderful day, and thanks for being part of the podcast. Bye.